last time we met, I promised you that at some point I was going to give you this handout. I decided to bring it today. I usually show at the beginning of the class, just to give you a feel for what finite element program structure is. And two things I want to point out. I think you can look it up on your own. But one thing is this assembly of force, vector, and stiffness matrix. That's usually what you learn when you take a finite element course. Most of us take a linear finite element first, and then we do nonlinear finite elements, and then we learn about iterations. So that's highlighted here in the dash. Every time you have plasticity, you're going to have nonlinearity. Even with the simple bilinear model. So that's going to require some iterations. But I wanted to show you that right at the heart of a program, there's always a material subroutine. And that's what you call when you want to evaluate the stress and the consistent tangent at every Gauss integration point. Okay, so I just wanted to give you that so that you see the whole thing, and in particular how this course relates to a previous course, let's say on finite elements. Okay, just to close the loop. Okay, last time we were looking at the ingredients of the one-dimensional model, and we stopped at a very important point where we said that f dot had to be equal to 0, and we call this a consistency condition. Right? Is that right? That's where we stopped, right? We said, okay, and the reason why we call it the consistency condition is simple. This is consistent with the Kahn-Tucker optimality conditions, right? That rather said, so this came from this idea that lambda dot times f equals 0 at every time. This is what we can call the Kahn-Tucker optimality condition. And then we decided, for whatever reason, to take the time derivative of these. And since this quantity is a constant equal to 0 all the time, then it boils down to f dot equal to 0 during plasticity. In other words, for lambda dots greater than 0, right? So that f dot doesn't apply in elasticity, obviously, because in elasticity, f or f dot are irrelevant. Okay, they're not applicable. Okay, that's where we stop. Any questions at this point? Okay, and what you see people do in plasticity is they exploit the consistency condition to solve for lambda dot, because then I also told you that the name of the game, the objective, in plasticity is to find lambda dot. Once we find lambda dot, everything falls apart. Okay? So, but it's one of those things where you find lambda dot, but in order to find lambda dot, you have to find everything else, right? So, okay, so it's not like you just find lambda dot and then you run with it. By the time you're done with lambda dot, you're done with everything. Okay. Okay. So, consistency condition. Okay. So let's go back. Oh, my handwriting is terrible today. Let's recall that our f in the bilinear model, the simple bilinear model that we're studying, is absolute value of sigma minus sigma y equal to 0, right? That's a yield function. And so we rewrote these as the sine function of sigma times sigma minus sigma y equals 0. So this is just a replacement for absolute value of sigma. And okay, now the name of the game is to find f dot. So we go ahead and evaluate f dot. So the first thing we get is the time derivative of sine sigma, and that's either, well, it's 0 because remember that sine sigma, the function, right, is +1 or -1, depending on whether sigma is greater than 0 or sigma is less than 0, right? It's just a step function. It's a constant. Okay, so this goes away. Then you get what? So this just comes along for the right. Then you get sigma dot, whatever that is at a particular time, minus sigma y dot, right? Because that is also changing as a result of plasticity. And my consistency condition says that all of these must vanish. Okay? So far, so good. Okay. So then I also recall my Hooke's law. At least the generalized one. Well, no, let's say Hooke's law, the traditional one, that says that sigma dot equals Young's modulus times epsilon E dot. But also by the additive decomposition, I know that this is epsilon dot minus epsilon dot P. Okay. And I replace that here, right? And I get that sine of sigma times E times epsilon dot minus epsilon dot P minus sigma y dot has to go. Then I recall the flow rule, right, which tells me that epsilon dot P equals lambda dot df d sigma, which in this case is lambda dot sine of sigma, right? And then I also recall the hardening rule, which says what? That sigma y dot equals h prime lambda dot. Is that right? Right? And now I take these two things and I plug them back into my current version of a consistency condition. So I get sine function of sigma times Young's modulus times epsilon dot comes along for the right minus epsilon dot P, substitute the flow rule, lambda dot sine function sigma minus hardening modulus times lambda dot equals 0. Collect terms and solve for lambda dot. Lambda dot, the consistency parameter, equals sine function of sigma times Young's modulus, all of that over h prime plus e, Young's modulus, all of that times epsilon dot. Interesting. So that says that my plastic multiplier, or my consistency parameter lambda dot, or the magnitude of my plastic strain rate, remember, that's what this is always equal to, essentially it's always proportional to the strain rate, the total strain rate, and then it's modulated by a quantity that is a function of my elastic properties, in this case, Young's modulus, but also my plasticity properties. Again, if you go back to, say, things like H equals 0, this drops, E over E cancels out, and you get that pretty much lambda dot is the same amount as epsilon dot should be. Right? H prime is pure plasticity. H prime equals 0 is pure plasticity. Right? So your total strain increment should all go to your plastic strain increment, or to your plastic strain. Right? Now, H prime going to infinity is approaching elasticity again, right? You go back to an elastic type process. So this remains bounded, the bottom goes to infinity, so this whole thing goes to 0, right? Even though this is non-zero. So lambda dot goes to 0. So that means that you are getting very little increments in plasticity, or essentially 0 increments of plasticity as this guy approaches infinity. Okay? So you're always in between 0, gaining nothing plastically, and approaching epsilon dot. You cannot have more than epsilon dot, essentially. Right? Your upper bound is epsilon dot, your lower bound is 0. Okay, for this guy. You see that? Okay, very important concept in plasticity, which you see very clearly in 1D because of the simplicity of the equations. But it will become harder later on. So this guy is strictly greater than 0 for plastic deformations. Okay. What else do I want to say here? So yeah, so this guy is called the plastic multiplier also called consistency parameter. Why consistency parameter? Because its value is consistent with the constraints implied by the consistency condition. That's how we got it, right? It's a natural result, or a consistent result, with all the ingredients of plasticity. Okay? Violate things like greater than 0, you violate some of the ingredients that we have established before. Okay? Okay, so now that we know what lambda dot is, we can go back. Now we go backwards. So we guaranteed, we said, okay, once you know lambda dot, you know everything, of course, because in order to construct lambda dot, you've used everything, okay? You've used the consistency condition, you've used the yield function, you've used the flow rule, you've used the hardening rule, you've used Hooke's law, you've used everything. So now, yeah, once you know it explicitly, you can go back and essentially unravel everything. So, epsilon dot p, the flow rule, lambda dot sine of sigma becomes, or just plug it in, the sine sigma cancel out, right? The sine sigma times sine sigma is 1, always, right? So you get E over H prime plus E epsilon dot. So then it follows, right, that this is greater than 0, thing in paren, right? So the sign of epsilon dot is the sign of epsilon dot P, makes sense. If I'm pulling, total strain is pulling, I would expect my plastic strain rate to also be pulling. If my total strain rate is compressing, I would expect my plastic strain rate to be in the compressive direction. Okay, and again, just like we saw before, things scale depending on what H prime is. Okay, so that's that. Then we go back to sigma dot, which is E epsilon dot minus epsilon dot P, right, from Hooke's law. And we get E times epsilon dot, and now we replace. And we get minus E over H prime plus E epsilon dot. Or in other words, I realize that I can move things out here. Well, wait. Did I do that right? No. Yes. Yeah, right. Okay, so let's see what happens. Yeah, this is okay. So then I get H prime plus, no, H prime, yeah, H prime over H prime plus E, or sigma dot equals E. I'm just going to put everything together. H prime plus H prime plus E. Okay? And therefore you discover that this guy is EG. Right? Your tangent slope, or your tangent modulus, is always equal to this plasticity. Again, what does that mean? When F equals 0 and when lambda dot is greater than 0, right? In the elastic regime, when F is, say, less than 0, you don't care about ET because ET is equal to what? Is what? You know. When F is less than 0 and lambda dot is equal to 0, what is ET?
Just E.
It's just E, okay, it's trivial. Okay, so note that it follows that H prime plus E has to be positive. Okay, and again, this goes back to the bounds of H prime that we spoke about before, saying H prime is always greater than minus E. So you cannot have softening that starts to creep into values of E negative. Remember, we said, remember when we spoke about the bounds for H prime, we plotted it against epsilon dot P, and I told you, okay, here is E prime, well, we can make this lambda dot same thing. So we said, no, what am I saying? This is lambda, sigma dot y, or sigma y, yeah, that's how it is. And this is H prime, and I said, your bounds here are upper bound plus infinity, lower bound minus E. And we said H prime lives in minus E if it Okay? Remember we did that? So that is consistent, once again, with this constraint. And the fact that then it follows that h prime plus e is always greater than 0. So the denominator here is always positive. Okay? Same here. Denominator always positive. This is always positive. So this whole thing here is always positive. The only guy that switches depending on whether you're in tension or compression is epsilon. Okay? Are we all clear? All right, so now, okay, so now we have sort of the basic ingredients that we have extracted, and I just want to do the last bit, which is the types of hardening that you might have. So, and again, this generalizes to essentially all models. So all models in plasticity essentially follow two types of hardening. The first type is called isotropic hardening. And as the name implies, and you will see multi-D, that just simply means that the entire surface or the entire elastic region expands or contracts equally. So if your, in this case, your yield strength, sigma y, increases by 5 kPa in tension, what do you think is going to happen to your sigma y in compression? It will increase by the same amount in compression, by 5 kPa. All right, so everything expands equally, or if it decreases by 5 kPa in tension, it will decrease by 5 kPa in compression. Now, there's another type of hardening that we will see as well, called the name just kinematic hardening. Thank you, Alex. Which it doesn't follow that rule. The way I see it is it takes the initial elastic region and it moves it. Okay, so again, if sigma y in tension increases by 5 kPa, everything moves up, let's say, which means that your compressive yield strength increased or decreased? Just decreased by 5 kPa, right? Because everything moved. You have the same amount of elastic region all the time, okay? So they're very different mechanistic models, okay? So, sigma y is the same in tension and compression, according to the isotropic model. So just like I said, so if sigma y increases by, say, some amount delta sigma y, the elastic region increases by what? By what amount? Delta sigma y, 0 or 2 sigma y, or 2 delta sigma y. Let's say the three options. Okay, come on, you're killing me. 2 delta sigma y, okay. So let's just do a graph here. So this is epsilon, this is y, And I'm sorry, I'm gonna use my drawing skills as best as I can with this. It used to be, looks like a pool stick of sorts, okay? So let's say this is my initial sigma y naught, which means that initially that's where I was. Okay, let's give this guy some elasticity. So beginning goes like this. Okay, so then we arrive here at the U point, and we go plastic, right? It's exaggerated, so we see. So let's say we started here at 0, we loaded in tension, got to the U point, kept loading, and then we decided to stop. And then we're going to unload. Okay, so according, oh, this is Young's modulus, right? So according to this model, you unload always with a slope of Young's modulus, but you just increase your yield strength from sigma y naught to some new sigma y. So according to the isotropic model, because you increase by some amount, call it delta sigma y, you must have increased your compressive side by the same amount. Right? So now you're here. Right? So that means that when I unload, so now I'm on this branch, I'm unloading. Okay, I just passed the 0 load threshold. I still have some residual plastic strain, but then I keep going. Now I go into the compressive side, right? And if my yield strength had remained the same, I would start yielding again as soon as I hit the minus sigma y naught point. Right? But because I have isotropic hardening, I don't. I keep going, and I'm still elastic. In fact, I can go all the way until I encounter minus sigma y. Right? And then I start behaving plastic again with a slope equal to ET again, but over here. So that's my AT. And then if I decide, for whatever reason, to stop here, go back to loading, I go back up. So this reminds me of a parallelepiped, right? Essentially a figure that whose sides are parallel. This is parallel to this, so this is all E. This line. This line is E, of course. This is ET. And this is ET. Right? That's the isotropic model. Okay? Whatever amount you increase in one side will get increased on the other side, in the compressive side. So your total, so again, here's your initial elastic region, right? Here is your current elastic region. Okay? The elastic region is alive. It's evolving. Okay? In the isotropic model, it's growing by the plasticity that you're imposing. Yes,
Was it just a coincidence that when you went back down, you hit minus sigma y at like exactly
Total
epsilon equals
coincidence.
0.
If I change E or anything, it won't coincide. So it was a coincidence that I encountered in the epsilon 0 axis, but it was not, of course, a coincidence that I encountered in the sigma y value. So yeah, I'm sorry, but I usually try not to make that happen, so that yeah, it doesn't become confusing.
How good of an assumption is isotropic hardening for different materials? Did you see it physically, or?
Yeah, that's a good question. So isotropic hardening, we'll write this down in a minute, is essentially very good for monotonic loading. Okay, so you're either going to load in tension and continue to load in tension, or you're going to load in compression and continue to load in compression for that particular material. Precisely what I did here, which is a cyclic load, right? I went 0 up in tension, and then I unloaded, and then I started to load in compression. This is exactly what you're not supposed to do with the isotropic model. Okay, it's not good for this. Yes.
So when we are in compression and when epsilon equals to 0, shouldn't it be minus sigma y naught?
Where? Here?
No, this.
Here?
Yes.
No, this is sigma y naught. This one is just minus sigma y, is whatever this was. The new point of yielding. That's the point. That we go way past, we no longer care about this point because the elastic region evolved. Okay, another way to see it is imagine that, okay, again, forgetting about physical behavior materials, the way I see this, or I imagine it, justifying it, why it would be like this is, let's say, your material somehow, this is saying your material somehow strengthens once it has seen a certain amount of deformation or plastic deformation in one direction. It strengthens in the other direction. You see? Which, okay, maybe if you're a granular material, maybe you rearranged in a certain way, and then once you start going, let's say, in compression, you're strong. In a metal, it's harder to imagine that, right? Because if you start pulling in tension and, I know, you get plastic deformation, it's hard to imagine that the material will be actually stronger as you come back and load it in the compressive side. But, okay. But that's essentially what the model is saying. Now, if you just keep doing it monotonically, the model is great because it just essentially enables you to keep growing your sigma y. But, okay.
So
yes.
should negative sigma y here be the lowest most point? Negative sigma y.
Yeah, it's your lowest most point for continuing to behave elastic. The moment you hit it, you start going plastic. Now let's say for ha-has, we didn't have to stop here. We could have gone this way. Let's go to another sigma y. Let's call it sigma y bar. Minus sigma y bar. Call it this one.
That will give us a new elastic.
Exactly. Then we go back up with what slope? This slope, right? So we start going up. So this line is still parallel to this line, parallel to that line. You keep going up, and now you don't stop at sigma y naught. You don't stop at sigma y. You keep going up until you encounter sigma y bar. And then once you hit it, now you're plastic again. So you hit ET, so now this is parallel to this. Right? And you keep loading till whatever you want. And now you have a new sigma y double bar. And you decide to stop there. You unload with E. And now we don't have board, right? We'll just keep going until we hit sigma y 2 bars in the negative direction.
So
Isn't
E here a little bit misleading then?
which E? This E or this E?
That one, yeah.
This one, why?
Because you have the dashed line going all the way to the acute angle rather than at minus sigma y.
Oh. That you should be hit the sigma y that lines. There's
So, I see what you mean. I see what you mean. Yeah. I beg your pardon. I made a mistake. Yeah. So this line, I see what the confusion is. This line stops here. Yeah, you're right. Thank you for pointing that out. And then this one stops here. You're right. Good point. Yeah. That's what I meant.
So one more thing to clarify for me. So the original one the original cycle that you drew,
Yes.
when you go back in compression, you now have a new sigma y, right? Like a sigma y star or something, because you've gone even further down now. So if you keep doing that cycle over and over, we just keep growing and growing.
That's right.
Okay.
That's right. That's
So
exactly.
it's not a closed loop necessarily. You can keep going.
No,
further.
you can keep going.
Okay.
Yeah, here we could have kept going. That's exactly
on the
right.
second.
Yes,
time you
to
went.
whatever point we, you're
okay.
right, yeah. I decided to close it
Yeah,
because
no,
I
just
wanted to, yeah.
Making sure that.
But yeah, so we can do these cycles whichever way we want. The point is, and the way to imagine this is that imagine that your sigma y is this sheet, and you are loading with your finger, like a loading vector. And what you do every time you want to push is you have to leave the sheet with you. And then wherever you stopped, you leave the sheet there, and then you go back to another direction. But whatever amount you move the sheet by here has to have moved over here. Okay? But these are two sheets that are there, and every time you're loading, you're pushing the sheets. Okay? With your finger in whatever direction you are loading. That's the way to imagine the model. Okay? That's isotropic hardening. Another way I explain it to people that sometimes is easier. It's probably the only case when multi-dimension is easier than one dimension. Imagine your elastic region, or the bounds of your elastic region being a balloon. So let's imagine that there's a balloon, you just happen to see one point of a balloon here and another one down here, but there's really a balloon. And so every time you touch, again, with your finger, the edges of the balloon, the boundary of the balloon has to inflate in order for you to go, let's say, from here to here. So if it inflated in this side, it must have inflated on the other side, right? Balloons don't decide just to inflate on one side and not on the other, right? It just sort of inflates isotropic. That is the isotropic model. The kinematic model, which we'll see in a little bit, the size of your balloon remains fixed. You have a steel balloon. Okay, you cannot inflate it. But your finger can poke at the boundary and translate the balloon. All right, so if your sheet, again here, went up in the kinematic hardening model, the other boundary must have gone up as well. So we'll see that in the kinematic model, this E naught remains constant. It just drags along. Right? The size of the elastic region is constant. Here, it's not. It keeps expanding. Right. So, yeah, so E naught, let's write it here. Is such that the close one at least is such that sigma y naught is included. And of course, E, which is always changing, is simply this. Okay, the beauty of this model or its attributes isotropic hardening. It's simple. That's why people love it. Okay? It's the simplest hardening model you would ever encounter. It's also sufficient. For monotonic loading. Okay? It's simple enough and sufficient enough. However, it's not good for cyclic loading. Okay, so if you want to use it to simulate the behavior of a structure after an earthquake, not good. Okay? It's going to make you increase your elastic region in a way that is unnatural. Right? If you want to simulate the cyclic loading again on an airplane, not good. Right? And so on. So be careful with isotropic hardening. Just make sure that you will always use it for monotonic loading, and things will be okay. Usually what you do in a model is you prepare the model for isotropic hardening, and then you take it to kinematic hardening. Okay? So you start simple and then you expand. Let's do kinematic hardening. So you get the picture between the difference between the two of them. Okay. So. Kinematic hardening. Okay. So you can expect right from the onset, it's going to be a little more difficult than isotropic hardening. So the way you generalize is that now your yield surface, before, recall that in isotropic hardening, your yield surface was a function of, your yield function F was a function of sigma and sigma y. Okay, now we're going to make that function still a function of sigma, but we're going to now call the internal plastic variable something else. We're going to call it alpha. So we've changed the plastic internal variable from sigma to something called alpha. And my yield surface now is going to look like sigma minus alpha, absolute value of that. All of that minus sigma y, but not sigma y naught. That has to be equal to 0 at yield. Okay, so notice the difference again. Compare with the isotropic case where this is the function. See that? Okay, the first difference is that there is existence of this new plastic internal variable. Remember, we define plastic internal variable as whatever evolves with plastic strain. This evolves with plastic strain in the isotropic model. Now, this evolves with plastic strain. This is a constant. Okay? All right, simple enough. Alpha has a name. It's called the backward, or no, the back stress, I'm sorry. Okay? Alpha is, like I said, a plastic internal variable. Okay, just like sigma y is 1. Yes, sir.
Doesn't mean that what we've talked about so far up to this point was for isotropic hardening.
Pretty much, but I'm going to recap everything, and then we'll see what applies to both and what only applies to one and what applies to the other one. Alpha equals 0 initially. Okay, just like sigma y equals sigma y naught at the beginning, alpha equals 0 at the beginning. Okay? And again, I just want to define plastic internal variable. So plastic internal variable. For example, sigma y, alpha, or anything, defined as any quantity that affects the value of the yield function. So the value of yield, and that may evolve with plastic strain. Okay, so the way to see plastic internal variables is that they affect your plasticity evolution, your plasticity formulation, and they evolve with plastic strengths. They don't evolve with elastic strengths. Okay? If there is no plastic strain, plastic internal variables do not evolve. Okay? So for instance, in the isotropic model, while we are on the elastic loading or in the elastic loading or unloading branch, my plastic internal variable, which is sigma y, does not evolve. Okay, my plastic internal variable sigma y evolves as insofar as I'm pushing the sheet, as I'm pushing the elastic boundary. Then it evolves. Okay, which means that I am engaging ET, which also implies that I have plastic strains. Okay? All right. Very important to get that clear. Because a lot of people I think that's one of the most confusing parts. Later on, not so much in the 1D, but even in the 1D, people don't have this clarity of when am I elastic, when am I plastic, okay? When am I accruing plasticity and therefore evolving my plastic internal variables?
When they code it, they tend to always compute the plastic part and
yes.
forget about the elastic.
They forget that there is a possibility for elasticity, exactly. I mean, there are all these little errors. Okay, so be aware. Okay, so I apply consistency. This has to be true for both of us. And I recompute this. This I've got based on this. So now I have sine of sigma minus alpha times sigma dot minus alpha dot, right? And this is 0, right? Because it's a constant, or the derivative of this is 0. So that must be 0. So the only way that this is 0, this is either +1 or -1, depending on the argument. So the only way that this will hold true is if sigma dot equals alpha dot. In other words, my back stress is a shadow of my stress, right? Whatever the stress did, increased by 2 kPa, alpha increased by 2 kPa. So this is like your friend that wants to be like you. Right? You buy a pair of jeans, this guy buys a pair of jeans. Exactly the same. Okay? This guy doesn't change. This guy doesn't care. Okay, it stays put. So this is the guy that essentially is the culprit for dragging the elastic regime, right? This will be that guy. Okay. And the way it's always going to do it is that it's going to say, all I care about is the distance or the difference between sigma and alpha. And that has always to be sigma y naught. Right? So in a way, that's the guy that fixes the elastic region for you. Okay? In the other model, it just says whatever sigma is, sigma y has to be. Right? So that's why if this guy increases by 100, this guy will increase by 100. And then everything will increase by 200. Here, no. Okay, so keep going. So again, in plasticity, I cannot overemphasize that, meaning f equals 0, lambda dot greater than 0, okay, you're engaging in plasticity, and then that's applicable. If you're not in plasticity, alpha remains at its previous value, okay? There's no evolution of alpha if you're in an elastic process. Okay, so epsilon dot p continues to be lambda dot df d sigma, also known as lambda dot sine function of sigma minus alpha. Okay, for the kinematic model. And don't worry, we will make a nice summary of the two so you see the differences and coincidences. Then we recall sigma dot equals sigma y dot, okay, equals h prime epsilon dot p in the isotropic model, okay? Then here we use the same thing and we say alpha dot equals sigma dot, right, in plasticity equals h prime, and then we replace what we know for epsilon dot p, lambda dot sine sigma minus alpha. Okay, so if you want, this is alpha dot equals h prime epsilon dot p as before. Okay? So again, I cannot overemphasize, just like before, this was true in the isotropic model, or essentially we wanted the absolute value of this guy in the isotropic model, right? So what I want to really emphasize is that your plastic internal variables always evolve with the plastic state. Okay? That's always the case. And there is a modulus, the hardening modulus, that simply scales that dependence. Okay? In this case, that modulus is a constant. In more evolved models, that modulus is a variable as well. Okay? But it's always the same structure. Okay, so that's that. So many people like to actually write this relationship this way. So they say, this is df d sigma, which is true. And then they say this is nothing but some scaling variable, just like lambda dot. And they call this, let's say, gamma dot. So they say alpha dot equals gamma dot df d sigma. You see this form for the plastic internal variable for the back steps many times in models. It's the same thing. Okay. Yeah, there's some plastic multiplier times some direction. Okay? All right. Let's keep going. So then, sigma dot equals E epsilon dot minus epsilon dot P, always will be. Replace. So in this model we get whatever, lambda dot H prime sine sigma minus alpha, correct? Plug that in, well, and then this has to be equal to, is that where I'm going? Yeah, to, let me see, let me make sure that that's where I want to go before I, yeah. That has to be equal, so sigma dot, remember, this is that, has to be equal to alpha dot, and we just say that alpha dot is this. Sorry guys, you're letting me do whatever I want here. Yeah, okay, yeah, I'm okay. Yeah, this is fine. So lambda dot H prime sine sigma minus alpha. Okay, sure. So then you collect terms and you find that lambda dot is absolutely equal to E times epsilon dot, all of that over and there's a sign here, isn't it? Yes. Well, it goes to the bottom, but it doesn't matter here if you write it at the top, right? Sine, it's just a sine function. And then here you get H prime plus E epsilon dot. So it looks form identical. That's why I'm confused, because I thought that the difference between this and the isotropic model was stronger, but it's not, okay? So compare the isotropic model. For some reason, I kept thinking that they're going to be different. So the isotropic model is E sine sigma over H prime plus E epsilon dot. Right. So they're in that. So many people write for both of them, they write lambda dot equals E over H prime plus E df d sigma, which is this, right? Times epsilon. That's one way to write both of them. Okay, we'll summarize everything, but for now, this is it. And then what do? Then we go back to Hooke's law. Replace these here. The signs disappear, right? And what do you get? Let me write it like this. E minus E squared over H prime plus E. You end up with the same ET as before. There's no difference. Okay, so ET same as isotropic model. Okay. And EP is the same. Pretty much everything is the same except for this small detail here. I'm a bit puzzled about because I thought the differences were stronger. So epsilon dot P, then you replace this here. The signs go away, Right, so you get the same thing with that before. As before. Okay, so they are pretty much the same thing. The only major difference is the introduction of a new plastic internal variable. That plastic internal variable is alpha. It also evolves with the plastic strains. And then once you plug that in to the model, everything falls apart as before. Let's do the diagram. I think that's the best way to visualize this model. So I'll try to do a better job at drawing the diagram. So let's try it here. Let's try to draw it together so you see it at the same time I see it. So that's my initial y-axis, initial x-axis. So this is epsilon, this is sigma. Okay, for the sake of argument, let's start with an initial elastic region like this, as before. Sigma y naught plus here, sigma y naught minus sigma y naught here. Okay, that's my initial elastic region. E naught. Okay, we start some loading increment here, same tension. Why not? And we can keep going until we hit the yield point. Okay. Initially, at this point, alpha is equal to what? 0. It remains 0 for all this time. Why? Because I'm elastic. I haven't reached plasticity yet. So all along from here to there, whether it's been 10 days, 10 years, or 100 years, alpha continues to be 0. The minute I hit sigma y naught, for the first time here, I get my first moment of f equals 0. Right? And then I continue to venture forward. I continue to increase. Let's say I tell my bar that I'm going to continue to increase the strain. Right? So my material is forced to go into plasticity. So ET engages. Say I keep loading. And I decide to do so to about half the value of sigma y naught. So about this point. Just to put numbers. So this is my first case of f equals 0. This is now 1.5 sigma y naught. So let's say sigma y naught was 10, this is 15 at this point. All right. Now I unload. I decide to unload. I could have taken it to 2 times sigma y naught, 3 times sigma y naught, whatever. I decide to unload. So I come back. I come back down with the same slope as E. Remember? And then in these models, by the way, so what is my value of f at this point?
Zero.
0. What is my value of f from here to here? 0. It was always 0. Right? I was always in plasticity. Now, let me ask you, what is my value of alpha here? This point. Right at this point. 0, right? What is my value of alpha here?
Delta sigma y.
I hear various responses. Delta sigma y. Okay. But that confuses me because there's really not a formal value of sigma y here. There's a more specific answer.
0.5 sigma y naught.
0.5 sigma y naught. I like that answer. That's exactly what it is. Okay? It has evolved to half of sigma y naught because that is how much sigma y changed. I'm sorry, not sigma y. Sigma changed in this plastic interval. Okay? And remember that alpha is a copycat of sigma. It wants to increase by whatever sigma increases. So sigma increased half of sigma y naught, alpha did the same. Okay, so at this point now alpha is 0.5 of sigma y naught. What's in the middle of this branch? 0.25, right? It will increase linearly between this point and that point. Okay. Now I start to unload. And then at some point here I ask you, what is alpha?
Same as it was before.
The same as it was right here, 0.5 sigma y naught. What is sigma y naught? Let's keep going, okay. Now, how far can I go if I keep unloading?
0.5 sigma y naught.
To 0.5 sigma y naught. Good. To this point. I unload and I hit this point, and I have run out of elastic region, right? Because my elastic region is here. And continues to be E naught. How much? In this particular case, 2 sigma y naught. Right? There's no more. So at this point, what is my value of alpha, of sigma, of f, I'm sorry, too many variables. It becomes 0 again, and the way to check again. So remember it says absolute of sigma. Sigma is 0.5 sigma y naught negative, right? Minus alpha. So minus alpha, alpha is 0.5 sigma y naught. So this whole thing together is, once you take the absolute value, is simply sigma y naught. Okay, and then it says minus sigma y naught. And of course this equals 0. Okay, so your yield function is satisfied at that point. What's the value of alpha? Well, we just said it. 0.5 sigma y naught at this point. Now you're stubborn and you decide to continue to load. So let's see if we can do this parallel as fast as we can. That kind of looks parallel, right? And you can keep going in that direction. There's no problem. The only thing is that alpha will have to evolve from this point forward. Is that right? So what is the value of alpha? say right at this point, when sigma is minus sigma y naught. Right? Good. So at this point, sigma equals minus sigma y naught, alpha equals 0, and f equals what? 0. It has always been 0 from this point onwards. Now, if you stop here and you reload, you go back to the origin. But you don't have to. You can keep going. Let's say we keep going to whatever, minus 1.5 sigma y naught. That's the value of sigma at that point. So sigma equals minus 1.5 sigma y naught. What's alpha? It's your new alpha.
Negative 0.5.
Negative or positive? Negative? Okay, what? Yes. And f continues to be 0. Why? Because minus 1.5 sigma y naught minus, which becomes positive, 0.5 of sigma y naught becomes 1 sigma y naught, and then you subtract the sigma y naught and it gives you 0. Okay, so you just went like this. Now let's reload. Let's stop here. We go up parallel to this, right? With E. Then, okay, so my value of alpha is minus half of sigma y naught. How far can I load up? How far can I continue to go? To 0.5, right? Right over here. 0.5 sigma y naught. This is the threshold now, the limit of my elasticity. Why? Because this distance is E naught, and this is 2 sigma y naught as before. And then if I engage this point, I go back like that. Okay. So these models are not difficult. They're accounting models. Okay. You account for things. Okay. You need to keep track of things. Things are evolving. And you have rules of evolution. You cannot just do whatever you want. Okay, alpha needs to evolve as sigma evolves. So this is the key in this model. Right? Alpha is attached to sigma in its changes. Sigma increases, alpha increases. Sigma decreases, alpha decreases. Okay? That's the key. Sigma y naught remains constant, and then everything else sort of plays along. Okay, in the other model, sigma y evolves. Okay, and that's the whole mechanism for evolving the model. Okay, but it's a big accounting job. That's all it is. So the things to keep in mind is, when am I elastic, when am I plastic? Here, elastic, elastic, elastic. Here, plastic, plastic. Right? ET, ET, E, E. When I'm on ET, my PIV is changing. When I'm on E, nothing is changing. Okay? That's it. Same for the isotropic one. So let's put everything together. but before that, yeah, I do have 10 minutes to do it. Let me very quickly give you the attributes of the kinematic hardening model, and then I'll summarize and then I'll end. Kinematic hardening. Its attributes. It needs to introduce this concept of backstress. Okay. It's okay for cyclic loading. So that's what it's used for usually. It's okay, but unnecessary for monotonic. Okay. So this need to introduce a backstress implies, okay, a higher amount of complexity than the isotropic model. Okay, the accounting is a little bit more tricky, right? So here I want you to know that whatever you increase in the yield strength in tension was taken from the yield strength in compression. So if you want to call it your sigma y, right, went from sigma y naught to 1.5 sigma y naught in tension. When you came back to it in compression, your sigma y available was only half of sigma y naught. Okay, so it's a zero-sum game. The kinematic hardening game. Whatever you took to give it to tension, you must take from the compression. Okay. That is called the Bauschinger effect. Okay. It has a name, and it's in the literature. Okay, concrete is well known for this type of game. They also call it, this degradation, meaning that in concrete makes a lot of sense. You start pulling your bar, and say cracks start to emerge in your material as you pull it. When you come back, your material is weaker. It has to be. Okay. So this sort of degeneration in your strength is seen in materials like concrete, and they're called, like I said, the Bauschinger effect. So let me just recap quickly, because I know it's a lot of information. So the big picture is the following. We're going to have an analytical model. This is the world of continuum. This is what we've been doing so far. All of the models that I've been describing right now are analytical. But then we're going to integrate those models, and we're going to get what's called a numerical. This is really what we can call the implementation. And it's really what we put within FEM. Most likely in your final element code, you're not going to put the continuum or the analytical model. You're going to put the numerical version. Okay? And then, okay, this goes into the mathematical theory of plasticity, and we saw that there is isotropic hardening, and then there's kinematic hardening. Okay? So every model, every paper you read out there is very likely going to start with the analytical model. And it's most likely going to describe either the isotropic hardening flavor or the kinematic hardening flavor. And then that model depending on the paper, may include its particular implementation of that model. And there are many, okay? There is an explicit version, there's an implicit version. There are many ways of implementing an analytical model. But at the end of the day, this class is about that numerical implementation. The analytical part is fine, but it's really the numerical implementation, the one that becomes useful to you. Okay? Not so much the analytical one. I've run out of time, but and I really want to do the summary well, so I want to stop there and rather have you ask questions and come back next class with a comparison between the two models and what ingredients are the same and what ingredients are different. No questions? Okay. If not, we'll come back on